Summary, the ramp. Again, we actually started this unit with a mini lab on doing a ramp problem. We're going to do it again in a slightly different way, and mixed problems. We've learned three formulas for uniformly accelerating objects. Uniform acceleration means the acceleration stays the same or it's constant. We rearrange the definition of acceleration to become the first kinematics equation. So here's acceleration. Here is the first kinematics equation. Next, we found the distance traveled by a uniformly accelerating object. And here's our equation. The displacement is 1/2 the sum of the initial and final velocities times t. And that's when these are your givens and also the variable you need to find. We then created this equation. Delta x is v initial t plus 1/2 at squared. That's where we're interested in vi, a, t, and delta x. And this is the second kinematics equation. Using these formulas, we can solve almost any problem for uniformly accelerating objects. Our first ramp lab, we found the car's acceleration down the ramp, but what's missing between this picture and what we had earlier? We were taking measurements as the car moved down the level surface here. But now we have more physics tools that enable us to calculate the acceleration by only making measurements when the car is on the ramp. Once again, we will ask and then tell you, what measurements do you need to make? What do you need to make the measurements? And what do you need to do for the calculations? So please take a couple minutes and write down your thoughts on that, pause the video, and come on back. First, we will measure the length of the ramp, delta x ramp, and that's going to be right here. That's the length of the ramp. And the time it takes for the car, which starts with an initial velocity of 0, to get to the bottom. And to be consistent, here's the rear wheel right here at the top. We won't stop our timer until the rear wheel of the car hits the level surface down here. We need to measure time, so we can use a stopwatch or your cell phone. And then to make the measurement of the ramp length, a meter stick would be a good idea. An excellent equation to use here would be the second kinematics equation. And why is that? Well, let's see. We know what vi is, it's 0, so this term actually cancels out. We'd like to find the acceleration, that's our given. We've measured the time, and we've measured the displacement. So we just have to rearrange that to solve for a. We start with the second kinematics equation, and the first thing we do is get rid of this term because vi is equal to 0. We then get rid of this 2 by undoing it, multiplying both sides by 2, right? Because we divided, so we'll multiply, and that gives us 2 delta x equals at squared, because these 2's cancel. Then just switch the sides. So I have at squared is 2 delta x, and we're interested in solving for the acceleration. So we need to get rid of this t squared, so since that's multiplying a, we get rid of it by dividing the left-hand side. Then of course we have to do the same thing to the right. And finally, we get the acceleration is 2 delta x over t squared. For the rest of this course, please use the problem-solving template as needed. For these problems, start with one of the three formulas from the summary page.